The last thing that we're going to look at in this section is Newton's law of cooling. Now, Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So it ends up being this differential equation: dy over dt is equal to k times y minus the temperature of the surrounding medium. If we solve this differential equation just like we did examples 1, 2, and 3, and how we came up with the formula y equals c e to the kt, we would end up with, for this particular differential equation, y equals c e to the kt plus the temperature of the surrounding medium. And I'm going to abbreviate surrounding medium. Now, instead of reinventing the wheel over and over again when you're doing these types of problems, you're just going to be using this formula when you're trying to deal with Newton's law of cooling. So be really careful, since we've just looked at the formula this way. C here is not the initial amount. Be really careful. C is not the initial amount because of the way that we had to work to get there with this differential equation. So let's do number 7, where it's asking us to find an equation and then figure out how much time it's going to take for something to cool down. So number 7 says, a container of hot liquid is placed in a freezer that is kept at a constant temperature of 20 degrees Fahrenheit. The initial temperature of the liquid is 160 degrees Fahrenheit. After 5 minutes, the liquid's temperature is 60 degrees Fahrenheit. Part A, write an equation for the temperature y of the liquid t minutes after it's placed in the freezer. In Part B, how much longer is it going to take for the temperature of the liquid to decrease to 25 degrees Fahrenheit? The first thing we want to do is look at what we're given and identify what these things mean. We know that we are keeping this in a freezer with a constant temperature of 20 degrees Fahrenheit, so that means that the temperature of my surrounding medium is going to equal 20 degrees. I know that initially the liquid is 160 degrees Fahrenheit, so that means that when T is equal to 0, y is equal to 160 degrees Fahrenheit. I also know that after 5 minutes, the temperature is 60 degrees Fahrenheit. So when T is equal to 5, y is equal to 60 degrees. That's enough information to do Part A, where we write an equation for this particular hot liquid placed into this freezer. So remember, we're using the formula y equals c e to the kt plus the temperature of the surrounding medium. So using the temperature of the surrounding medium and this first bit of information, we can solve for C. We say 160 is going to equal c e to the k times 0 plus the temperature of the surrounding medium, which is 20. So solving for C, first subtract 20 from both sides, and you get 140 is equal to c times e raised to the 0. Well, e to the 0 is just 1, so that means that c is equal to 140. So now we're going to use this bit of information and this bit of information to solve for k. We know that 60 is going to equal c, which is 140, e raised to the k times t, which is 5, plus the temperature of the surrounding medium, which is 20. Now let's solve this for k. So subtract 20 from both sides, and we get 40 is equal to 140 e to the 5k. Dividing both sides by 140 to solve for k, we end up with 2 over 7 is equal to e raised to the 5k. Taking the natural log of both sides to solve for k, we end up with the natural log of 2/7 is equal to the natural log of e raised to the 5k. Well, here natural log and e will cancel, and we just have that the natural log of 2/7 is equal to 5k. Solving for k, and we get k is equal to the natural log of 2/7 all over 5. Therefore, part A, the equation would be y equals c, which is 140, e to the k, which is this natural log of 2/7 over 5, t plus the temperature of the surrounding medium, which is 20. Part B is asking us, when is the temperature of this liquid going to end up being 25 degrees Fahrenheit? For part B, we need to figure out what is T so that y is 25. So plugging it into the equation we just came up with for part A, we end up with 25 is equal to 140 e to the natural log of 2/7 divided by 5 t plus 20. Just like before, the first thing you had to do is subtract 20 from both sides, and we have 5 is equal to 140 e to the natural log of 2/7 t over 5. Divide both sides by 140, and we get 1 over 28 is equal to e raised to the natural log of 2/7 t divided by 5. Taking the natural log of both sides to solve for t, the natural log of 1 over 28 is going to equal the natural log of e raised to the natural log of 2/7 t divided by 5. Well, the natural log and e are going to cancel on the right-hand side, and we end up with the natural log of 1 over 28 is equal to the natural log of 2/7 t divided by 5. Solving for t, first multiplying by 5, and then dividing by the natural log of 2/7, and we end up with t is equal to 5 times the natural log of 1 over 28 divided by the natural log of 2 over 7. Plugging that into a calculator, we end up with t is approximately alpha y equals for numerator and denominator, and we end up with 5 ln of 1 divided by 28 divided by ln of 2 divided by 7 is approximately 13.3 minutes. Now, we have to be really careful because the question actually asked us, how much longer will it take for the temperature to reach 25 degrees Fahrenheit? So we know that 5 minutes have already passed. So again, we know 5 minutes already passed. Therefore, how much longer would be 8.3 minutes. Because if it takes 13.3 minutes to reach 25 degrees Fahrenheit and 5 minutes have already gone by, we're going to have to be waiting another 8.3 minutes. That's it for exponential growth and decay.